Hello, everybody. So in Beachboard this week, I have like your regular PowerPoints, and there's some lecture data that typically when I would have like an hour and 50 minutes to go over everything, we would have done an example. Um, but because I didn't want to like drag out the lecture and kind of like let you guys sit with the conceptual stuff first, what I did is I made the regular activity video has a review of this lecture data. And then I included the output that you should get. Um, so you can like practice running the tests as I go through them in the video and then check your output. This should be correct. It is an SPV file, so it should directly open in SPSS. Just a note. So if you're using like virtual lab, you would have to open virtual lab before you open that file. But instead of going through the video or the activity step by step, I use the lecture data to like describe how the flowcharts work. And then that's kind of your instruction for you to work on activity 8. So it kind of sets you up so you know what you're doing. And then per usual, there's a quiz this week. And then all of your resources are down in the supplemental area. But I just wanted to point that out because it's a little bit different than what I usually do. So with that being said, today's lecture isn't going to take up a whole lot of time. At least it shouldn't, because generally we've covered most of our concepts. We're just expanding on them this week. So I'm hoping that that will be nice for everyone. Okay, get my stuff worked out. I need to do favorite memes and gifs and dad jokes and stuff because they make us happy. So I found this dad joke. It said, my wife is kicking me out because she's fed up with my South American animal puns. I said, okay, I'll pack in my bags. Ah ha ha. Knee slapper. Thought this one was funny too. Doctor, your body has run out of magnesium. Me, OMG. Yeah. Periodic table coming back. And then I saw this one. I thought it was really funny. But also, if you really look, I don't know if someone doctored Andrew Jackson's face, but I was kind of impressed. So, anyways, down to business. We're talking about factorial ANOVAs this week. And I put this GIF in here because this is the second to the last lecture. So we're in the final stretch here. You guys have almost survived this class. But factorial ANOVAs are going to be, if we follow our flowchart, when we have 2 or more independent variables. So we've kind of been floating in this area for the last several weeks where if we're looking at t-tests, there's 1 independent variable, it has 2 levels. If we go to ANOVAs, 1 independent variable, but 3 or more levels. And now we're looking at factorial ANOVAs in the case where there's 2 or more independent variables, but we don't have the presence of a covariate. And I'm not going to get into what covariates are yet because we will cover that next week. Very briefly, usually I would have done clinical measures in chi-square as well as ANCOVAs and MANOVAs. But I feel like in online learning, those particular tests are probably like way too difficult to try to explain through an online format. So factorial ANOVAs is like the last one you'll be responsible for knowing how to run in SPSS. I still would make sure you know how to do one-way, simple and repeated measures ANOVAs, though, because those will be integrated into the third exam as at least conceptually as part of how you figure information out about ANCOVAs. But again, we'll go over that next week. But the main difference between one-way ANOVAs and factorial ANOVAs is the number of independent variables. So, like I said, 2 or more, okay? And there's different types of factorial ANOVAs based on how your independent variables are collected. So technically, there's 3 different ones that we look at. And the examples that I've listed in this slide are 2-way ANOVAs. And I'll kind of explain that in the next slide, I think. But if all of your independent variable samples are between subject design, so we call it independent or between design, that means we have an independent 2-way ANOVA or a 2-way between ANOVA. There's a lot of different ways we can list it, but this would be an example of where all of your samples are between subject collection. We could have a purely repeated measures factorial ANOVA as well for a 2-way where you only have 2 independent variables. We could, and both are collected with a within subject design. We call it a within factorial ANOVA, a 2-way repeated measures ANOVA. But in either of these cases, right, we kind of treat how we collect our samples very similarly in comparison to 1-way and 2-way ANOVAs. So if we have a between subject design for an independent variable, that variable has to meet all of the assumptions of a between subject design. So for 1-way or simple 1-way ANOVAs, we said that's a between subject design where each sample of our independent variable or each grouping has been collected independent of other groups. So in this case, if we had a between design, every single group between both variables are completely independent or separate from each other. So in that case, each variable would have to meet homogeneity of variance. Similarly, with the repeated measures ANOVA, when we have a within subject design, we said that our variance or different scores of the variance between samples needed to be relatively equal, and we labeled that as sphericity. So the assumptions apply based on how your samples are collected, but basically you're not learning anything new with respect to assumptions. You just have to be able to identify how are the subjects collected and then apply those assumptions with that categorization. And so these are like if we're fully independent or fully repeated measures, but we can also have a mixed design where some of your independent variables are measured with split subjects or separated subjects, in other words, a between subject design, or some of your subjects could be a within subject design. So in that case, when you have a mixed design factorial ANOVA, you would have to meet the assumptions of both homogeneity of variance for the between subject factor only, and then you would have to meet sphericity for the within subject factor. And this will make a little bit more sense when we go into our examples, but kind of just pointing out that it's nothing new, we're just adding another layer. So don't freak out because you guys are smart, okay? But like I said, there's different types of factorial ANOVAs, and they're named based on how many independent variables there are. So I put this one in parentheses because it's not a factorial ANOVA, but kind of just to get at the concept that in a 1-way ANOVA, we had 1 independent variable. In a 2-way ANOVA, there's 2 independent variables. 3-way ANOVA, 3 independent variables, okay? In our class, we're just gonna stick with 2-way ANOVAs because the analysis is complex enough, and at least in papers that I've read so far, I've hardly ever seen a 3-way ANOVA, just because that's a lot of variables to look at. But just point out, we're only going to work with 2 ways in our class, and there's different ways of going about labeling those. so the design of the study, and you may have seen this in empirical papers before, if they used a factorial or mixed effects design, but it's denoted by the number of factor levels. So variable levels, if you want to look at a synonym for factor. So basically, if you have something that says like, oh, we used a 3x2 type of factorial ANOVA, that's indicating that there's two independent variables. One of those independent variables has 3 levels. The other independent variable has 2 levels. Okay, so if you had a 3-way ANOVA, let's say we're keeping 3x2, right? You could have a 3x2x3, 3 numbers indicating 3 independent variables. So, like I said, we'll stick with the 2-way format, but just to kind of wrap your head around how they're denoted. Okay, and like I said, usually you won't see any more than 3 independent variables just because the analysis gets really messy. And you'll see why in a little bit, but this is how we name them. So if you see factorial ANOVA or 2-way ANOVA, in our class, those are kind of synonymous. Okay. Any questions so far? We're doing okay. All right. So let's do an example. So we've got a study looking at different levels of intensity for training programs. So we're classifying those levels of intensity as low, medium, and high. And we want to see if those levels of intensity, as well as their, or if they have an effect on strength development for males and females of different ages. Okay. So what is our dependent variable? You can pop it in the chat or unmute yourself.
The effect on strength development?
Right, so strength development, we're not necessarily saying how we're measuring that, but generally we would assume this is ratio type data, right? So maybe we have some type of strength assessment or a series of strength assessments and measure strength in some way. So yeah, we can generalize it and say strength development. How many independent variables do you guys see in this example?
3.
3. Do you want to identify one of them?
Low. Or 25 to 35.
So this would be like in reference to the training programs or the intensity. Is that what you're saying?
Honest, I don't know what I'm saying.
Okay. So I think you're on the right track. There are 3. So you weren't wrong in saying that.
Would it be the ages?
Ages is definitely one. To Chris's point, because I kind of gave it away, the intensity or level of intensity would be another one. And then does anybody see the third one?
Gender.
Gender. Okay. Or actually, to be more inclusive, we could label this as a person's biological sex. Okay. We had a conversation about that in our department today. So thought it was very interesting. Anyways, that's besides the point. We have 3 independent variables. Okay, so we're saying intensity, our level of intensity, gender, and age. How many levels of each of these would you say we have? So let's start with intensity of the program. How many levels do you see?
Just 3.
3, right? Low, medium, and high. Okay, how many levels of gender?
2.
2, right? Male and female? Okay. And then how many levels for age?
And 3.
3, right? So 25 to 35, 45 to 55, 65 to 75. Okay. So it's important that you identify, right? And this is kind of the general stepwise process that I'll have you guys do when you figure out what type of factorial ANOVA you're looking at. Because based on this information, oh, actually, I'm skipping ahead of myself, but start thinking about that. What is the study design? In other words, like how did we collect each of the variables? Or I don't think I gave enough information, but we can kind of speculate. Or maybe that's not what I want to ask. No, let's go backwards. So study design being like, how would you denote the design of the factorial ANOVA based on this concept here? Like based on factor levels.
3 by 2 by 3.
3 by 2 by 3. Okay. And then let's say, because this is the part where I was getting ahead of myself. So let's say that the way that we've collected people, because we obviously know males and females are different. So would that be a between or within subject design for that variable? Anyone? Males and females. Let's see, someone put something in the chat. 3-way factorial ANOVA, absolutely. But we have to be a little bit more specific by means of how we collected our samples, and that's what I'm trying to pull out of you guys right now. So males and females are different. So is that between or within?
That's between.
That's between. Okay, so we've kind of got one locked down. Age groups, obviously people who are 25 cannot be 45, so that would also be a between subject factor. Don't know why I'm holding those. And then as far as in the level of intensity, I left this a little bit open-ended, but let's say that for each age group and for each gender, people were only sorted into one level. So they only did low, they only did medium, or they only did high intensity. Would that be between or within?
Between as well.
Between as well. Okay, so if every single one of these variables are a between subject factor, how might we label this factorial ANOVA, or what would we call it? 3-way factorial ANOVA, yes, but more specifically,
Between or independent?
Mm-hmm. And because there's 3 variables, we would say we could, again, many different ways, and I kind of go into this in the video for the activity this week, but you could call it a 3-way independent ANOVA. That's probably the simplest way to put it. You could call it a 3-way between ANOVA. You could call it a 3 by 2 by 3 independent ANOVA, or a 3 by 2 by 3 between ANOVA, right? So as long as you're somehow pointing to 3-way or 3 independent variables, or what characterizes those independent variables, as well as commenting on how the subjects were collected, right? So either indicating it's a between subject factor, a within subject factor, or using repeated measures or independent, you're pretty much good to go, right? So 2 main things you have to consider when labeling. So hopefully that was helpful. Okay. Any questions on that? looking good. Okay. So, I don't know, animations got messed up on this slide. But like I said, for this class, we're only going to do two-way ANOVAs. I just wanted to give an example of how a three-way would work, because there's still a possibility you guys could get questions on how, kind of the example I just gave. It'd be more of a research scenario where you list out what the independent variables, dependent variables, how they were collected, what you would call it type of concept. So conceptually, three-way ANOVAs aren't out of the picture, but procedurally, two-way ANOVAs are what you're responsible for, okay? So similar to a one-way ANOVA, we're basically just looking at mean differences between groups. But we're gonna have three main results versus in a one-way ANOVA, we have one main result or one main effect, right? And in a two-way ANOVA, because we have two independent variables, we have two results that are related to those independent variables. So let's say independent variable A is going to have a main effect. Independent variable B is going to have a main effect. And then we're also inserting an interaction effect between both variables A and B. Okay, so it's kind of looking at the dependency of one independent variable on another, and I'll go into that a little bit more in a few slides. But if each of these has a p-value in the output, that means each of them has a null hypothesis, okay? So when you're going through factorial ANOVAs and I ask you, what is the null hypothesis of the main effect? Like, you have to extrapolate that and say, well, if there's two independent variables, that means I have one effect for each independent variable, and I also have the interaction effect between those two variables. So this is why we stick to two-way ANOVAs, because if you have a three-way ANOVA, you actually end up having 7 results that you look at, because you would have one main effect for each independent variable, as well as the pair comparison between each independent variable, as well as a three-way effect. So you can see it gets really complicated really quickly. So two-way is plenty for our class, okay? But in terms of the null hypotheses, right, you can read these very similarly to how you would read a one-way ANOVA. And the main effects are basically one-way ANOVAs. So as far as interpretation goes, you guys should have this locked down, right? So if we're looking at the main effect of independent variable A, we're basically saying that that variable or that intervention or I don't know what other treatment is the other word I was wanting to look for, okay? But that intervention or that variable manipulation has no significant effect on the measured dependent variable, right? That should sound relatively familiar. You can also use the no significant mean differences, right, between the groups of that independent variable if you like that method better. But basically what we do when we look at main effects of a single independent variable, we've classified people based on two independent variables, right? So if we take the example we just looked at and we were only considering gender and the intensity level, right? And let's say we want to look at the main effect of gender first. That's simply going to look at strength development between males and females, regardless of the intensity level that they trained at. So when you look at these results of factorial ANOVAs, you kind of have to take them with a grain of salt because you're excluding information on how you categorize those people in the first place, okay? Similarly, if we took that same example and we looked at intensity level, right? Let's say that's our main effect B, right, or independent variable B. We would say intensity level has no significant effect on strength development, right? But that's also looking at low, medium, and high intensities regardless of the gender that participated. So you have to remember main effects only consider the groupings of that independent variable, right? Kind of excludes all other classifications on how you might have collected your subjects from the beginning, okay? Which is why in a factorial ANOVA, we have an interaction effect. So that, again, this is looking at how dependent is one variable on another. And this one I feel like is kind of difficult for some students to grasp, or it has been at least in previous semesters. So we'll look at some examples of this in a little bit. But basically, the null hypothesis is that independent variable A has no significant interaction with independent variable B in terms of the dependent variable. So if we used intensity level and gender for a dependent variable of strength development, our null hypothesis for those variables would be that intensity level has no significant interaction with gender in terms of strength development. Okay, so that's how we would apply that there. So similar to other tests that we've done, you take the null hypothesis, the generic one, and you just plug and chug what your variables are into that null. Okay. I actualized this. Oh, I'm so on top of it today. So I kind of took out the age concept so that we just have a two-way, right? But this is kind of actualizing what I just said, right? Where we have two main effects, one of the intensity of the training program, right, on strength development, one on gender and strength development, and then the interaction effect between the two. Whoops, didn't mean to do that, okay? So if you wanted a reference to what I was saying, this is it, right? But main thing, two independent variables means two main effects plus one interaction effect on how they work together, okay? Whoa. Any questions on the conceptual part? Okay. So then we go into the interpretation of results. And I've written this out many different ways so that hopefully one way or another will click. So it is a step-down process. And this is where the flowcharts will really help you guys because they map out what to do when things happen. So first you have to check the significance or the p-values, right, of the main effects as well as the interaction effect, okay? If any one of those has a p-value greater than 0.05 or a p-value greater than alpha, whatever that may be, your analysis stops for that particular variable, okay? So that's why in this one, it's kind of like an all or nothing for how I wrote it here. So if none of your main effects are significant, you accept every single null hypothesis, okay? But if you have at least one significant effect, either the main effect or interaction effect, where p is less than 0.05 or less than alpha, your analysis continues, but only for the significant effects. So let's say that your main effects are significant, but your interaction effect is not. In that case, the interaction effect would, you accept the null hypothesis saying there's no interaction between the two variables or two independent variables. And then you would still look at the post hoc tests for the main effect since those were significant, okay? So if you have no significance, you stop the analysis for that effect. If you do have significance, we do as normal and we have our post hoc tests, okay? Or pairwise comparisons. So this will be pairwise comparisons for the main effects. And then technically for interaction effects, we look at what's called simple effects, but they will also pop up as pairwise comparisons in your SPSS outputs, okay? But basically that's just kind of, when we do interaction simple effects, that allows us to layer our samples into each other so that in the conditions of one independent variable, we can look at if there's significant differences of the other independent variable. And I know that wording probably just went one ear and out the other, but I have examples, so you will be fine. I added in this flowchart, and I know it looks like a lot, but it's just another version of the flowchart that I've already given you. So again, you start with 3 main effects, right? 2 for the independent variables, 1 for the interaction, okay? So you treat the main effects as you would a one-way ANOVA. Just think that you're isolating out 2 one-way ANOVAs, right? And when you have a significant effect, you look at the posthocs to find your significant pairs. That's everything you've done already. So these 2 sections you have experience doing. For the interaction effect, we have to do something weird in SPSS because SPSS doesn't automatically calculate for interaction effects. It just tells us, is the interaction effect significant? But then it doesn't tell us how it's significant. So we kind of have to alter what goes into SPSS. But you could have 2 different cases, right? When the interaction effect is significant, you have to look at the simple effects in 2 different ways. One, by looking at significant differences between groups for independent variable A within levels of independent variable B, and then flip that vice versa. Okay, so this would be like if we're using our intensity level and gender example. Let's say in our ANOVA test, both of those came out, or there was a significant interaction effect. So if we're using intensity level as independent variable A and gender as independent variable B, one of our simple effects would look at significant differences between our intensity levels based on gender, right? So that would be saying, what's the difference between males and females in a low intensity? And then what's the difference between males and females at a medium intensity, right? So you kind of see how we start to look deeper into the categorization of our groupings. And we can flip that, right, and look at it the other way, where we're looking at significant differences between intensity level based on gender. Okay, so within females, what are the pairwise comparisons between a low to medium intensity? What are the differences between a low and high intensity? What are the differences between a medium and high intensity? And then we would look at all those same pairwise comparisons within a male group, right? So in either way, we've got these significant pairs that are going to be coming out. They're just based on a certain classification, okay? So I've kind of added in some more descriptions of this because it is kind of hard to grasp onto. And I go through this process 3 different times in SPSS in your activity video, so it should make sense. But like I said, SPSS doesn't automatically look at the pairwise comparison. And I know this is kind of small, so when I do the video recording, I'll zoom in on this. But basically, this is called the syntax of your output. And so we have to edit that syntax. And so usually what happens is you've got, basically we're looking at this estimated marginal means area, because those are your pairwise comparisons, usually that you would use in a repeated measures ANOVA. And in our case, we're going to use the estimated marginal means for every single type, whether it's independent, repeated measures, or a mixed factor ANOVA, okay? But in any case, you see there's estimated marginal means for program. So this is giving you your post hoc tests for independent variable A. We have estimated marginal means for time, at least in this example, right? So that would be your post hoc test or pairwise comparisons for independent variable B. And then we have the interaction effect. And what's in this green box doesn't usually exist in SPSS. So we have to go in and look at the syntax, and then we edit it based on how we want to analyze our data. And this one only has one line of this syntax, but basically we're saying you're going to compare one of the variables using the Bonferroni adjustment, so it'd be the same as both of the other main effect pairwise comparisons. But then you would go further and add another line where you say, I want to compare program as well. And I do go deeper into this in the video, because doing it and talking about it at the same time definitely makes more sense than having a still picture. But I've also kind of expanded a little bit on what that syntax means. So generally when you see, like A times B or that notation, that's indicating you have an interaction effect. Okay, so that's what you're going to look for when you have your syntax open. And then, like I said, you'll have two lines that you basically add to the syntax. When you see compare independent variable A, or in this case, the example is time, okay, that means you're comparing time within whatever the classification is for your second independent variable. So in this case, we would be looking at program, right? So this would say, let's say we had 3 different time points where we measured heart rate. I'm just pulling this out of my butt, but 3 time points where we measured heart rate, and we're using various programs like HIIT training or weightlifting or whatever to see how those programs affect heart rate, okay? So just say we have 3 programs and 3 time points. So compare time means that I will be looking at the significant differences between time points 1 and 2, 1 and 3, and 2 and 3 within each of the programs, okay? And we could flip that. If we wrote compare program instead of time, that would look at the significant differences between programs A, B, and C within the given time points. So, like I said, video really makes more sense of this, I think, but generally that's how you read the outputs, okay? As far, or at least that portion for generating the syntax. The rest of the PowerPoint is basically SPSS instructions on how you would run each test. And there's also practice problems included. These are the practice problems that I go through in the activity video. So if you want, I would recommend maybe going through each of these questions to see if you can answer them before you watch the video, just for practice on identifying variables and types of variables, how many levels, etc. And then I go through the analysis process with you in the video so you can see how that works. Okay. But does anybody have any questions so far?
I have one question.
Yeah.
So when do you know when to count as another IV level or IV?
So it usually I'll give some information on how data is collected. So in terms of like the example I just gave you guys with intensity level, like you can, sometimes I'll separate out that like I did in the sample question where I was like, oh, it's medium, low, high, right? And you can clearly see that each of those are different. That one probably wasn't the best example in terms of figuring out if things were between or within subject designs. But in all of the other examples I give you guys, it's very straightforward, and there should be, it shouldn't be open to too much interpretation.
Gotcha.
Right?
So just kind
Yeah.
of like don't overthink it either.
Yeah. So I think the examples that are at the end will be helpful in helping you figure that out. And then you have 3 more examples in the activity, plus examples in the quiz this week. So hopefully you'll get enough practice doing that.
For sure. Thank you.
Yeah. But I wanted to go over one more thing, my whiteboard. You guys can see that, right? Okay. So I just wanted to go through the process of analysis one more time. Any one of the ways I give this to you, I'm hoping one of them holds. So, and I'll zoom in on this in the recording too, so that's easier to see. But again, if you're looking at the main effect analysis, you essentially are doing this part twice, one for each independent variable, right? But I'm saying, like, let's look at independent variable 1 or main effect of independent variable 1. And I'm going to say I have 3 levels of that. So group A, B, and C. Okay. When you look at your main effect, you still have to look at the assumptions for that effect. So that was kind of one of the first slides of the PowerPoint where I was saying if you have between subject, so let's say that this is a between subject independent variable where all of the groups are different, you would have to meet the assumption of homogeneity of variance. And then for our class, we assume we have normal distribution, random sampling, and that our variables are matching to what we would have in our decision tree. But if this was a between subject variable, we'd have to have homogeneity of variance. If this was a within subject variable, we have to meet the assumption of sphericity, okay? So assumptions always come first, because then you figure out, do I need to make any adjustments to my degrees of freedom if my samples aren't similar enough, right? But also remember, the analysis of this main effect excludes all other classifications that we would have with independent variable 2, okay? So only looking at the groupings based on groups A, B, and C for this given independent variable, right? And then basically the main effect is interpreted like a one-way ANOVA. So we're looking at, are the means of group A, B, and C equal to each other? And if we have a significant effect, then we look at our pairwise comparisons, right? If we have 3 groups, we'll have 3 comparisons, looking at how mean A is different from mean B, group mean A is different from group mean C, and how B would be different from C, right? So again, this part should seem familiar. When we add the interaction effect, we have independent variable 1 as well as independent variable 2. For simplicity, I said the groups of independent variable 1 are A, B, and C, and the groups of independent variable 2 are groups D, E, and F. Okay? So as far as the ANOVA is concerned, right, for the interaction effect, that p-value we get in the ANOVA table just tells us if there is an interaction effect, okay? So if we don't have a significant interaction effect, we just don't investigate it any further. If we do have a significant interaction effect where p is less than 0.05, that's where we look at the pairwise comparisons for the interaction, which is where you change the syntax and then you get all of that complicated stuff I was just showing you. But when you break it down, you'll end up getting 2 charts. And they will, and this is kind of messy, but in a way, right, you'll have one chart that shows you significant differences between groups of independent variable 1 within groups of independent variable 2, right? So in groups D, E, and F, do you have significant differences between groups A and B, A and C, B and C? And these 3 comparisons are exactly the same as what we're up here, but now we're just dividing this data into a given group based on variable 2 groupings. okay? And so these comparisons, these three here, are repeated in each of the groups for variable 2, okay? And then we flip that and we look at, are there significant differences between the groups of variable 2 based on groupings of variable 1? So then we have basically the same thing, right? Where we look at 3 pairwise comparisons for our second variable based on classifications of our first variable. So hopefully that makes sense. And hopefully I did my screen right so that I can zoom in on that picture, because right now it's showing that Ernie is talking. So yeah, anyway. All right. That's all I have for today. So short lecture. Hope you guys enjoy the rest of your evening and email me if you have questions.